Hey guys, welcome back. In this video we are going to cover Castle Unit 6 Activity 2, which is on the use of ammeters as well as the quantitative measurement of the flow rate of charge through a circuit. So first I want to talk about what is the ammeter, what is charge flow rate again. So remember, charge flow rate, the flow rate of charge, or the rate of the flow, is not a speed. It's not telling us how fast the charge is going. It's telling us how much charge is moving through the wires. So it's actually giving us a quantity, not a speed, if that makes sense. So this ammeter, it doesn't measure the speed of the charge, it measures how much charge moves through it in 1 second. Okay, and the amount of charge that moves through something in 1 second, that unit is called the amp, or the ampere officially. Okay, and 1 ampere is 1 coulomb of charge every second. So it says that a coulomb is a certain amount of charge, and if it's 1 amp, then that much charge is moving through in 1 second. Now, this first circuit that we see here is our simple standard circuit with just the battery and 2 bulbs. And you see I have the ammeters here positioned like it has on that worksheet. And you notice that each ammeter reads the same value, 0.45 amps. Now that should make sense because, as we've talked about before, in a series circuit, the amount of charge that comes out of one wire in the loop has to go into the next wire in the loop. It can't just disappear. It can't get stored. If that circuit is in steady state and the pressure is remaining constant over time, then the flow rate through every bulb and through every wire must be the same in series. Okay, so you see 0.45 amps. We're going to use that since this is our, quote, standard circuit. We'll use that as kind of our baseline value. The second circuit is very similar to the first one, except for that it's using long bulbs instead of round bulbs. And you probably remember that the long bulb has a higher resistance than the round bulb does. Since it has a higher resistance, that means that the flow rate should be less. And we see here that 0.09 amps is obviously less than 0.45 amps. You see again, since it is in series, we have the same flow rate of charge, the same current through each wire. And you see that these arrows that represent our current, they are moving pretty slow through the whole circuit. Okay, number 3 is modified again so that instead of these bulbs being in series, they are in parallel. And we have this first one, which is letter A on the sheet. That is our trunk wire. And we see that our trunk wire now has a much higher current, 1.8 amps, where on our standard circuit it was 0.45. So adding these bulbs in parallel has made less resistance and therefore more current through our trunk wire. We also see that in each of our branches we have less current than we did through the trunk wire. That's because the current through the trunk wire, it's splitting into these 2 branch wires. You see on these really nice, cool arrows, it's moving very, very fast through this trunk wire, but it is moving slower through these wires here. And you see that once both of these wires merge again at this ammeter, they do have to speed up again so that they can move through it. So that's showing that more charge is moving through here, this trunk wire, than there is in either individual branch. Okay, number 4, same deal as the last one, except for again with long bulbs. We see again each of these branches is half of our trunk wire, and they are exactly half because both of these bulbs have the same resistance of 50 ohms down here. Okay, so since both of these have the same resistance, we do have the same amount of charge flowing through both of them, and it is half of the amount of charge that's moving through our trunk wire. Again, since the long bulbs have a higher resistance than the round bulbs, I know that these still look round, but the resistance is higher. These are our long bulbs. Okay, since that resistance is higher, our total amount of charge flow is less, even if the battery is the same. Okay, number 5, I apologize for the kind of broken looking nature of this, but it was hard to get it all to fit and look smooth. But here we have 4 round bulbs in series with each other. Something that you should remember is that if you add more bulbs in series with each other, then you are adding more resistance to the circuit, which means that naturally, if there's more resistance in this circuit than there was in our standard circuit, then we should have a lower rate of charge flow. And if there's twice as many bulbs, then there's probably twice as much resistance. So we should have maybe half as much charge flow. Okay, so you see here on the first one with 2 bulbs in series, we had 0.45 amps through everywhere in the circuit. And here on number 5, with 4 bulbs in series, we have half that, 0.22 amps of current through each wire. And again, you should notice that every single one of these is the same in series. They are all 0.22 amps because you can't have more charge flowing out of one bulb than is flowing into the next bulb. Okay, numbers 6 and 7 are similar to each other. They are that mixed bulb circuit with 1 round bulb, the dimmer one, and 1 long bulb, the brighter one. As we've discussed before, in series, it doesn't matter if the resistances are different. The current has to be the same through each wire. So the current is 0.15 amps through the whole circuit. It does not matter that these 2 bulbs have different resistances. Remember, the fact that those 2 bulbs have different resistances, it doesn't change the fact that the flow rate has to be the same, but this long bulb does use more of that voltage, more of that electric pressure. So the long bulb here, the brighter one, has a larger electric pressure difference because it has a larger resistance and therefore needs to have more pressure in order to get the same charge flow as the top bulb has. Number 7 is the same circuit, but with the long bulb and the round bulb switched positions. Okay, so same discussion as I just gave of the last one, but with the bulbs switched positions. You see that the current is the same. The position of the bulbs does not matter. Okay, here on number 8, we have 4 long bulbs in parallel. Again, you see that the current is relatively small because even with all 4 of these in parallel, the resistance is still pretty big compared to just a couple of round bulbs. Okay, now there is more current than our standard circuit at 0.72 amps through the trunk wire and through the battery. Okay, and again, that current does split up. You see it splits into these 4. Each one of these 4 has a pretty slow flow rate, but you can see that through the battery the flow rate is higher. Okay, each one in parallel does have the same current because it does have the same pressure difference or the same voltage as we discussed in the last activity. Now, something that we didn't or have discussed a little bit is that as we add in parallel, the voltage of the battery should actually decrease. And that is because of the battery's resistance. Right now I have the battery listed with a resistance of 0 ohms. Here it is with 1 ohm. Did you see the current change? With 2 ohms, 3. So as the battery gets more and more resistant, the current gets smaller through the trunk, but it's still the same current through each one of these long bulbs because they each still have the same pressure difference, but that pressure difference gets lower when the battery's resistance gets higher. Okay, and finally, this one's really misshapen and is missing some ammeters because it only let me put like up to 6 or 7. So there, this is a little bit different than the one that we have, but what we've already seen is that the amount of current, the flow rate through each bulb in a series must be the same. So on this last one, 0.06 amps is going through each one of those ammeters on the far right, and 0.09 amps is going through each one in the middle, and 0.18 amps through that single bulb there. We see the trunk wire in and out of the battery right here and here is the same at 0.33 amps. And you may or may not notice this right off the bat, but if you add 0.18 to 0.09 to 0.06, that does all total up to 0.33 amps, which means that the total amount of flow, all of that charge that's coming through this ammeter here, it's splitting into 3 different sections, but they are uneven. This section here, this last branch that has the most resistance, does get less of that flow than the first branch, which has the least resistance. Okay. Just real quick, I'm going to discuss our consensus here for this activity. I do have the transcription of the consensus on the assignment page as well, so do make sure that you take that down. But the first point is that the ammeter must be connected in series. I suppose I didn't really discuss that at the beginning, but since it's measuring the charge flow rate, that charge does have to move through it in order for it to be measured. A good measurement tool doesn't interfere with the circuit, so if it's going to let charge move through it, that means that it can't actually impede the charge as it moves through, which means that our ammeter must have very little or no resistance, just like the wire, because if it did have a resistance, then it would impede that charge flow and change the flow rate through the circuit. So the ammeter has no resistance and must be connected in series. When it's connected in series, the ammeter readings are consistent with our flow rate predictions based on arrow tails. So what I'm saying is that more arrow tails means more charge flow. Less arrow tails means less charge flow. We have been doing that in the past. We have less arrow tails on our long bulbs because they have a higher resistance, so we have less flow rate, and we did see that. That is consistent. In series, the individual flow rates are the same at every point around the loop. Okay, so if I went back to this series circuit here, the individual flow rates are the same through all points in the loop. Whereas in parallel, like in this last one here, the flow rate in each branches add together to equal the flow rate through the trunk wire and the battery. Okay, so here's our trunk wire. That splits into these 3 sections. All 3 of these would add it together to be the same as the flow rate through our trunk wire. Alright guys, go ahead and finish up that worksheet and submit it. Have a good day.